Thank you for this day. Thank you for your love and kindness. Thank you, Lord, that you're the one that draws us to yourself. None come to the Son unless they're drawn to the Father, and you're good about doing that. And I pray for this whole school, for everybody here, faculty, staff, a whole lot of us, that you would do some drawing. Not only wait until next week, but even now, that we might all be helped to seek you wholeheartedly. That, Lord, you just open up our hearts and minds to your will. Not so it's just a feeling, but so it's real, so we make connection. And I pray your blessing on this class, right here. You can do that. You can make something meaningful today. And I pray you would in Jesus' name. Amen.
Amen.
So this is the part that some of you got this down. This is the last thing on Baumgartner's deal. Global seismic imaging of our globe have shown images of the mantle that reveal a ring of anomalously cold rock at the bottom of the mantle in an area about 2,200 kilometers down beneath the subduction zones that surrounds the Pacific Ocean. There appears to be density variation, and variation to be is large, even 4% is large, and the colder pocket of the rock down the lower part of the mantle, however, is very near the temperature of the material at the Earth's surface, which suggests that it got down there recently, relatively recently, not millions of years. If it happened millions of years ago, it should have acclimated to the same temperature, but it isn't. It's still significantly very near to the temperature of the mantle on the Earth's surface. So that suggests, it doesn't prove, but it just suggests that there could have been rapid subduction, and that's a remnant of rapid subduction. That was once part of the oceanic crust that during the flood was subducted rapidly into the mantle and moved its way down and is sitting there nice and cool for somebody to check out and say, hey, could be. So geologists are trying to make these differences chemical, trying to say, well, it's a chemical difference in the material, but the most straightforward interpretation is that it's simply colder material. So that's that. And so, earthquakes. That's what I just passed out to you.
That's not earthquake, that's an earthquake.
What makes an earthquake?
Chocolate and peanut butter. That's part of the reason. So anyway. So even though the side of this dessert, they cause some to tremble and shake. A real earthquake is which there's a trembling, shaking of the ground caused by sudden release of energy stored in the rocks beneath the Earth's surface. So there's a sudden release of energy. I don't know. Oh, that's fine. Oh, that's good. Looking for a cheap pencil. I don't like to do these to good pencils. So, if you take a pencil, it's just too nice to do with this too. So if you take it like this, and you start bending, and you don't necessarily see anything, but pretty soon, it'll suddenly snap. Release energy. Energy is released from that. Well, that's the same thing. In earthquake, there's some release. There's some, like if you had subduction, as we showed in the video last time we met. So you had the lithospheric oceanic lithosphere subducting under the continent, and the continent was clicked a little bit and then it releases suddenly, and that's what you have. You have a sudden release of energy, which depending on how great it is and where it is, it can result in tsunami, it can result in a lot of different things. So stress is put on rocks through the great internal forces which can produce strain, bending, and or change in volume of the rock. Strains build, so does stored energy in the rock. So it doesn't happen all at once, it builds up. The San Andreas Fault, which we saw a picture of the other day. So rock is moving, trying to move, building up pressure to move. One side is moving one way, the other is moving the other. They're not moving anything, they're stuck, and all of a sudden there's sudden release. Well, that sudden release is a release of energy. So this energy release is expended in moving the rock into a new location and in the form of seismic waves. So this is subduction, Eurasian plate. So this is, as this moves this way, friction is obviously generated here. This little lip here is pulled down, and finally it's released, and that release displaces, it phases the waters above it, displaces the water, and you've got tsunami, depending on the size and magnitude of that. So you need to know this kind of stuff. The focus is the point where the earthquake or waves originate. Okay, the focus is in the earth. If this was the earth, this little rectangular piece, if this was the earth, the focus would be along this fault where this thing is released. Say this was binding here, this was going this way, this was going this way, for example, and all of a sudden there was a release. Well, that happened right here. That's the focus. The epicenter is the point straight above the earth. Straight above. This is the surface of the earth here. The epicenter is at the surface of the earth, directly, perpendicularly above where that took place. So that is pretty easy to calculate. You can triangulate it. We'll talk about that later. So focus is in the earth. Epicenter is on the surface. Epicenter is right above where it happened, but it's on the surface of the earth. The earthquake didn't happen here, it happened here. But the place on the surface of the earth right directly above it, that's the epicenter. So, and it makes a difference. The epicenter is going to be the epicenter, but it does make a difference on how deep it is. It makes a difference in how we feel it. So most quakes are associated with movements on faults. Okay, a seismometer is a detection instrument. It doesn't record anything. A seismometer is something that just detects the movement. A seismograph records the movement. It's a seismometer with the paper and pen attached. So if something happens, you get a record of it. The first one, the seismometer, is just an instrument. It's just, you could have a seismometer, you could have something fastened to the ground in a certain place that has a string and some weight on it, and when that starts moving, well, that could act somewhat as a seismometer. But if you put a pen on it, it could be a seismograph, a crude one, but anyway. And a seismogram is the record that it produces, the paper with pen marks on it. Seismographic stations exist all over the world, and they're used to determine the strength, location, and depth of focus. So seismographic stations, they exist all over the world. I don't think I used the video because it had, the only great part was it showed how many seismic stations there are globally. They're everywhere. They're everywhere. There's not just 5 or 6. There are everywhere. So it helps to locate where these things are. And then and you need to know what these are. These 3 waves. There are many, many kinds of waves. Yes?
the video with the QR code on there? On the book? Or
Oh, you mean the one that was in the handout, that one?
the text?
That might have it. Well, that'll show it. But I saw a video that showed it all of a sudden, all over this part of the earth that was showing. It was great. But you're gonna need to know these three waves. There are many waves. Oh, nice. So, if you had, let's say you put off an explosion here, and you'd have waves that would go, well, you have inner core, outer core, so you'd have waves that are going like this. And if this was a P wave, if this was the first one, compression wave, travels the fastest. So where it hits here, it ricochets off this way. And it goes here, it could go a number of different places. And they have all these measured, all these are lined up. It could be very, I mean, that's why you could take many classes of this as an undergraduate, this seismology. You could do undergraduate degree in seismology, and you'd have to understand many of these different waves, what they do, when they reflect off, when they go through different medium, like they go through the mantle, the outer core, the inner core, it deflects them, and you can tell when they're deflected, you can tell what they've gone through. But those are P waves, they're compression waves, they travel the fastest, okay? P waves are the quickest. S waves don't go through liquid. S waves wouldn't go through this liquid part. They would reflect off just like this. They wouldn't go in here through the core and out. There would be a shadow, actually, there would be a shadow on the other side of the earth because they could not pass through liquid. They don't do it. They're shear waves. And then surface waves travel the slowest. But they can do the most damage. So, P waves, S waves, surface waves. P waves fastest, surface waves slowest, S waves don't go through liquid. Okay, so this, you have a rope and you shake it, you get this loop going all the way to the end if this is pivoted here. So you've got a motion like this, going through and going this way, like this. You can see this is in your book. That's an S wave. A P wave is more like a slinky. It's pulled apart, then it compresses, and when it compresses, this moves here, this keeps moving here. So you get this kind of movement here, you get this kind of movement here. So you get a different movement. And that'll become somewhat important. Well, P and S waves all start out from the earthquake at essentially the same time. But S waves are slower. Remember, P waves go faster than S waves. They all start off the same bang. They both move forward, but P waves travel faster. So as they move away from the earthquake, they separate because one is moving faster. So you got one that's moving faster. So the farther they travel, the longer the span is between the two. So if you are recording, if there was an earthquake so if there's an earthquake here, and you have a recording station here, and you get this, the farther this is, by the time that P wave gets there, and then an S wave is traveling along, there's going to be a time factor between when the S wave gets there and the P. The P is going to get there faster. Well, you can tell from that time differential how far away this thing was. There's a chart in your book, and I think we're gonna cover it well, we're gonna cover it here as well. How you can tell, because they're two different speeds. And the surface wave is gonna travel the slowest of them all. So, oh yeah, I guess I could do this one.
Lisbon was one of the richest European capitals. On All Saints' Day of 1755, most 150,000 residents were in church. The city began to shake.
Yeah, I mentioned this morning.
Worshippers rushed outside calling to God for protection. Then came a second, more powerful shock. Buildings collapsed, crushing the crowd below. Those that survived faced a tidal wave. Then a fire that burned on for 3 days. 60,000 people lost their lives. Lisbon's great medieval buildings and masterworks of art were incinerated. There was something to be learned here. First-hand accounts revealed that the earthquake had produced two distinct types of motion, a tremulous vibration followed by a wave-like undulation. The understanding of these vibrations would be advanced by the development of the seismograph. It was an instrument that could record and display these seismic waves. A heavy pendulum remains stationary because of its inertia, even as the world all around it shakes. The seismograph was able to record two distinct types of waves. A primary, or P wave, arrived first. This was followed by a secondary, or S wave. The faster P waves moved through the earth like sound waves, compressing ahead, expanding behind. S waves are slower because of a lateral shearing component, which is particularly damaging to buildings. The first half of the 20th century saw the development of more sensitive and accurate seismographs to record earthquakes. The Vickert recorder was state-of-the-art in 1910. Seismograms remain the basic record of an earthquake. From their tracings, a seismologist can calculate not only location, but also the direction of slip and the energy released. Sometimes even the length of the rupture. The amplitude of the largest wave is measured to determine the magnitude of the earthquake on the scale developed by Charles Richter. Because the range of energy release is vast, the scale is logarithmic. The difference between the magnitude 6 and 7 is 10 times. Between 6 and 8, 100 times. By the early part of this century, seismographs were linked in a global network. With data from 3 observatories, an earthquake anywhere in the world could be pinpointed through triangulation.
So triangulation. So the earthquake happens, and somebody that's got a seismograph here can say, okay, from the distance, the time that they got the P wave to the time they got the S wave was so far. That means this earthquake is somewhere within this circular area. They don't know where it is, but it's somewhere this far away. This one could say the same thing. Unless it goes black. Well, it starts over. Like this. This is what triangulation is. So, I've got a seismograph, somewhere I get an earthquake symbol, well, it tells me if that was drawn, if that was right in the center, it would say it's somewhere out here. I don't know where it is, but mine says it's this far. Let's say it's 100 miles from where I am. And then somebody else over here has another reading, and theirs says it's 1,500 miles from where they are. And then the third one says it's about 75 miles from where they are. Well, where those three cross, that's where it is. That's triangulation. You got the distance, you get the reading. The difference between the P waves and the S waves, you get a difference. The length of that difference here tells you it's this far, here tells you it's this far, there tells you it's this far, and where those 3 points meet, then that's the epicenter. That's the place on the top of the earth that it is. This thing could be very shallow or very deep, but nonetheless, that's where it is. That's triangulation.
Accurate seismographs to record earthquakes. The Fuca recorder was state of the art. Seismograms remain the basic record of an earthquake. From their traces, a seismologist can calculate not only location, but also the direction of slip and the energy released. Sometimes even the length of the rupture. The amplitude of the largest wave is measured to determine the magnitude of the earthquake on the scale developed.
Now, this is the Richter scale, Richter
The
method.
range of energy released.
There are different methods for using it. Richter is good enough.
The difference between the magnitude 6 and 7 is 10 times.
That's what logarithmic means.
And 100 times.
Just between 8 and 9 would be another factor of 10 larger.
Global network. With data from 3 observatories, an earthquake anywhere in the world could be pinpointed through triangulation.
So, and here's your book, well, your book has something like this as well. So, this is, you got a P wave. It comes down to here. The S wave, there's a curve based on the speed that they travel. And generally, they travel different speeds through different medium, but if they're traveling through functionally the same medium, they're gonna change over time. So, you've got this and this. When you first get a record of the first P wave, and this is the first, so this recording station that was here would get the P wave here, and then the S wave here. This recording station up here would get it here and here. So this distance would be a very short distance, this would be a longer distance, and this distance here, from here to here, is the farthest away. So you can calculate then, using these, okay, it should be this far away from Ion, this far, and you can put those together and come up with where the distance is, how far the distance is away, where where the epicenter is. Okay. It's frozen. This is. There we go. Okay, so that's what I just went through. So where they all connect, where they all meet. Somebody calls and say, okay, I've got an earthquake, it's this far away from me. And they're all connected, so somebody else says, yeah, it's this far from me, it's this far from me, well, you can go to a plot and find exactly where that thing is located. Okay, surface waves generally produce more property damage. So the surface waves are not, the S wave and the surface wave are not the same thing. The surface wave is the one that goes along the surface. It goes the slowest. And when it vibrates, the Alaskan earthquake, that lasted, I don't remember how long it lasted in 1969 when it happened.
3.
Yeah, a long time. So you've got heavy duty movement for a long period of time. Well, it does a lot of damage.
I think it was like, I don't know when I told me.
We've got that. I've got it somewhere here. Actually, I have recordings of that. So surface waves produce more property damage than body waves because they produce more ground movement and travel slowly, so they take longer to pass. That would be something you should probably remember. P waves travel about 4 to 7 kilometers a second, depending on the density of the material. So P waves, the thing that causes an adjustment in how fast they travel is the density of the material. And so continental crust has a density, you don't know that, but 2.7 grams per centimeter. A P wave would travel about 6 kilometers a second, which is about 3.6 miles a second, 216 miles a minute, and about 12,960 miles per hour. So the P wave is doing some traveling through the continental crust, almost 13,000 miles an hour. In other words, a P wave would cross the United States in about 14 minutes. An S wave, not the surface, but an S wave would travel a little slower through that, about 2.4 miles per second, so it'd only go about 8,640 miles per hour. So you've got a difference of 5,000 miles an hour, a little bit more, between the two, how fast they're traveling. So the P wave travels first, S wave follows that, and the surface wave would be the last. So across the United States, you'd have one travel about 14 minutes, the other one 21 minutes, so you'd have a 7-minute difference in the length of the bird, in the length of the United States. So, it would come to you in a flash of what you learned in this class, and you would pull out your travel time curve, and while not knowing where the earthquake was located, you know how far away it was away from you, and that's what we did. That's what that triangulation does. It tells you where it's located on the surface. A distance how far away it is from you, you get 3 places, and they can point where that is. So, I'm gonna do this one here. I'm gonna stop here. This is just a little bit.
everybody, it's Mike, and today we're going to take a quick look at the
Probably don't know Mike,
distribution of
but
seismic
he's the
activity
guy that did
across the surface of the Earth. And I'm going to do this using this great simulation, which you can check out on your own. The link is down below in the description. Now, what we have here is a somewhat zoomed in look at the Earth's surface focused on the Atlantic Ocean. You can see North and South America there on the left-hand side or the west, and Africa and Europe and Asia over on the right-hand side. And so the first thing we're going to look at is earthquakes. So if we go back to 1980, so
Let me just maybe mention, when we were talking about the continents and how they're separated, and this is pretty loose, this is probably not as accurate as it could get, but you see this little lighter area, that's not just the coast, that's an extension of where the continent actually is. Before it starts falling off, that piece, when that's included in mapping the continents, that extension, not the coast, I can't think what the name of it is, but when that's extended, these continents fit a lot nicer together, a lot more nicely together, like this. This is the coast. You don't see this is underwater, this little lighter piece. That's underwater, but it still extends out and it's part of the continental shelf is this. You don't see, it's underwater, but you don't see it. But when that's included in putting these continents together, it fits a lot nicer. If you just saw the continents like they were, it fits okay. But with that included, it fits a lot better. We talked about that before, but I just thought I'd tell you.
about 44 years ago, and we plot the location of every earthquake on the surface of the Earth. That's what we're going to see right here. So let's take a look at that now.
That's up to 1980.
And there you have it. Now, just to point out a couple of things, the size of the circle plotted, the diameter, reflects how strong the earthquake was, or the magnitude of the
Big
earthquake.
one.
So the bigger the circle, the stronger
Big
the
one.
earthquake. The colors, the red, orange, yellow, blue, etc., reflect the depth of the earthquake focus. So how deep within the Earth's crust the earthquake actually happened.
Not epicenter.
Now, what you'll probably
Focus.
notice is that earthquakes, while they're happening all over, do not occur randomly on Earth's surface. And in fact, there's a reason for that. They happen in these predictable locations, which end up being the boundaries between the Earth's tectonic plates, or lithospheric plates. Think of it this way. The Earth's surface is broken into giant pieces, solid slabs of rock called lithospheric plates, and those plates have boundaries between them, and those boundaries are where the earthquakes and other seismic activity occurs. So let's add some evidence to this. I'm going to go ahead and add on the locations of volcanic eruptions. Let's take a look. So now you see all those triangles. Those are the locations of active volcanoes on Earth's surface. And you'll notice, for the most part, with a few exceptions, they tend to happen in these same regions along plate boundaries. Now, what I'd like to do is overlay this map with the actual boundaries themselves, so you can see how the seismic activity aligns with those dividing areas. So you see those colorful lines that have been added in? Those are the actual plate boundaries. Those are the spaces where the tectonic plates meet one another and where motion causes seismic activity. But understand that along those boundaries, that motion might look different depending on where the plates are moving. So in some cases, plates will be converging or colliding with one another, while in other spots they might be diverging or separating. And then finally, we might see transform boundaries where they're sliding past one another. And there are some very different surface characteristics that we see depending on the type of boundary. Before we look at that though, let's add in some arrows on this map to see the way the plates are moving in this particular context. So if you look at all those arrows, you can see that in some places plates are coming together, in others they're moving apart, and in others still they're sliding past one another. Let's go ahead and put in the names of the individual plates, as well as the names of the continents and oceans, just for clarity. And there we have it, a nice complete view of the seismic activity and plate boundaries making up the surface of the Earth. But let's explore a little deeper here and see what actually happens at these plate boundaries in terms of the actual earthquakes themselves. So let's begin in the mid-Atlantic ridge. So this is a plate boundary in the middle of the Atlantic Ocean. I'm going to zoom in first. So here I am in the North Atlantic Ocean, and you can see this band of earthquakes happening right down the center there, where we have two plates that are diverging. What I'm going to do is we're going to draw a cross-section to see the depth of these earthquakes as you cross over from one plate to another along this boundary. Let's do that now. So here you see the top of this interesting cross-section. That is the surface of the Earth. And as you go down below, you're going deeper into the crust or the lithosphere. And what you'll notice by the location of the red dots is that the earthquakes are all very shallow. They're happening right at the surface at this type of boundary. Now let's keep this in mind and then contrast it with a different type of plate boundary. So I'm back here in my full view of the Earth with all of my seismic activity, and this time let's look, instead of at a divergent boundary, let's look at a convergent boundary. So I'm going to zoom into an area known as the Peru-Chile Trench. This is a region where oceanic crust is sinking underneath continental crust on the west coast of South America. So first, let's zoom in a little bit. And now let's draw our cross-section. Now here, you'll notice something very interesting. Remember, at the divergent boundary, all of the earthquakes happened up at the surface, and that's because the plates were simply pulling away from each other. And that causes some tension, and that tension is released in the form of earthquakes. But at this type of boundary, we have oceanic crust, which is made of dense, heavy basalt, sinking underneath continental crust, which is made of less dense granite. And when that happens, the earthquakes follow the subducting plate. So you'll notice that, yes, we have a lot of activity at the surface, but as the plate subducts, we also see deeper and deeper earthquakes. These regions tend to be much more active and violent as the plates converge with one another. Now, before we finish up, let's take one more look at the third type of plate boundary, which is a transform plate boundary where plates are sliding past one another laterally. And the best example of this is along the west coast of North America at the San Andreas Fault. Let's zoom in there now. Here we go. Now, try and predict in your head what's going to happen with the depth of the earthquakes here. Will they be deep, shallow? Keeping in mind that in this location, the plates are not colliding or diverging, but rather they're sliding past one another. Let's go ahead and draw the cross-section. And it looks fairly similar to our divergent boundary. And the reason all the earthquakes are happening up at the surface is because no plates are sinking or subducting beneath the lithospheric crust. And so all the earthquake tension is released up at the surface. Now, there is one other interesting region that we could take a quick look at, and that would be another type of convergent boundary where plates are colliding. But in this case, instead of having oceanic crust, heavy, dense basalt, sinking underneath continental crust, let's look at a region where we have continental to continental convergence. And one of the best examples of that would be the Himalayas and the northern boundary of India. So let's zoom in there. Here you can see very clearly that convergence zone where the Indian continent is colliding with the rest of Eurasia. So it's continental to continental collision. And so instead of one plate subducting due to its higher density, in this case, the two plates are made up of the same material. And so when they collide, the land essentially crumples upwards. The result, of course, the Himalaya mountains, but also quite a bit of seismic activity in the form of earthquakes. Let's draw a cross-section here and see where those earthquakes are happening. Now you can clearly see it's a very active region, and there's definitely more depth to the earthquakes here than what we saw at the divergent or transform boundaries. But still, they tend to be limited up to the surface region. And again, that's because we don't have any subduction taking place. And so there you have it, a quick look at where seismic activity occurs on Earth and what those earthquakes actually look like in terms of how deep and strong they are at different types of plate boundaries. This is a great simulation from the Concord Consortium. I encourage you to check it out using the link in the description below. Thanks for watching.
Not now. So, this is a 5-minute thing. So, last night when I was looking for things for what I did this morning, and I came across this in my email, and it's a 5-minute thing by Dennis Prager, and I don't know if you watch Dennis Prager at all, y'all, but he's good. He has a lot of these 5-minute videos that are excellent. And this I thought was one.
Why are so many young people unhappy? To cite just one example, Reuters reported in 2019 that
Has to do with
suicidal
the assignment I gave a while
severe
back.
depression and rates of self-injury among U.S. college students more than doubled
He's not a Christian, he's
over
a
less than
Jew,
a decade.
but thoughtful.
And unhappiness is hardly confined to Americans, as the social commentator Kay Heimowitz recently wrote, Germans are lonely, the bon vivant French are lonely, and even the Scandinavians are lonely. The British Prime Minister recently appointed a Minister of Loneliness. People have more money, better health, better housing, more education, and live longer than at any time in history. But people, especially the young, are unhappier than at any time since data began to be collected. Why? There are any number of reasons: increased drug and opioid addiction, less human interaction because of constant cell phone use, and young people's fears for their future are the most widely offered explanations. But the biggest reason is the loss of values and meaning. Let's begin with values, and I'll focus on America. The United States was founded on two sets of values, Judeo-Christian and American. This combination created the freest, most opportunity-giving, most affluent country in world history. This is not chauvinism, it's fact. That's why people from every country on earth have wanted to emigrate to America, and still do. Chief among the American values was keeping government as small as possible. This enabled non-governmental institutions, Kiwanis, Rotary and Lions clubs, book clubs, the Boy Scouts and Girl Scouts, bowling leagues, music societies, and of course churches, to provide Americans with friends and to provide the neediest Americans with help. government has gotten ever larger, many of these non-governmental groups have dwindled in number or simply disappeared. Another set of values is referred to as middle class or bourgeois values. These include getting married before having a child, making a family, getting a job, self-discipline, delayed gratification, and patriotism. All of these have been under attack by America's elites with the following results. The majority of births to millennials are to unmarried women. Yet according to a 2018 Cigna study, single parents are generally the loneliest of Americans. The percentage of American adults who have never been married and who have no children is at an historic high. Then there's patriotism. Until the 1960s, Americans grew up loving their country, admiring the founders, and believing in America's values, most especially liberty. Americans did not ignore the bad parts of their history, but they were wise enough to recognize that what made America exceptional was not its flaws, which were all universal, but its virtues, which were not. This strong American identity provided generations of Americans with roots, community, optimism, and meaning. Which brings me to the most important reason for all this unhappiness, a lack of meaning. As Viktor Frankl, the renowned Austrian-American psychoanalyst, wrote in his masterpiece, Man's Search for Meaning, aside from food, the greatest human need is meaning. And nothing has given Americans, or any other people for that matter, as much meaning as religion. But in the West, since World War II, God and religion have been relegated to the dustbin of history. The result is that more than a third of Americans born after 1980 affiliate with no religion. This is unprecedented in American history, and it's even worse in Europe. Maybe, just maybe, the decline of Protestantism, Catholicism, and Judaism, those great providers of meaning, is the single biggest factor in the increasing sadness and loneliness among so many young people in America and around the world. A 2016 study published in the Journal of the American Medical Association, JAMA Psychiatry, found that American women who attended a religious service at least once a week were 5 times less likely to commit suicide. And common sense suggests this applies to men as well. Young people have been told God is nonsense, their country is essentially evil, their past is deplorable, their future is bleak, and marriage and children are not important. Why are so many young people depressed, unhappy, and angry? It's not capitalism, or income inequality, or patriarchy, or even global warming. It's having no religion, no God, and no country to believe in. And what does that leave them with? No meaning. But there is always Instagram. I'm Dennis Prager.
So, if you've ever, Prager, you have 5-minute things, and usually he does speak in some of them, but they have 5-minute things on almost everything. And it's thoughtful. It's just thoughtful. He's not saying that's the way it is, but it's reasonable if you consider it. Okay. So here we are, back in intensity. Of course, we might have just left it, but here we are, looking at another angle. So, how much and what kind of damage the quake causes? That's what intensity is. How much and what kind of damage the quake causes. So you look at the buildings down, you look at the highway. It uses a modified Mercalli scale. The problem with this method, in evaluating this, is different locations, so different intensities. Damage to structures depend on what they were built on, how they were built, and who estimates the damage. Benefits are, it doesn't take any instruments. You just go out there and you look at things. And what you see, you evaluate. You say, okay, what kind of ground was it built on? What are they built with? How it was designed? What did they build with? Wood, concrete blocks, non-reinforced walls, whatever. They could evaluate that. And then you're the one that's estimating the damage, and you just make an estimate. So you don't need any instruments for this, you just need your old eyeballs. But that's why you could get differences in intensity. Magnitude is the amount of energy released at the earthquake's focus. So within the earth, not the epicenter on top, but within the earth's focus, how much energy was released there? And that uses a Richter scale. Now there's another scale in here, I'm not sure I'll get into that, but there's another one that's probably more commonly used right now, but there's nothing wrong with this for you to get a picture of what they're doing with this anyway. Because that's all I'm trying to do with this class, is give you a kind of a brief picture of what's going on, how they're evaluating this. And when you see Richter scale, you're looking at seismograms, which tend to be, and they've made adjustments in this, above 7, they tend to be inaccurate or give a too low a reading, but they've got they've got methods of adjusting that right now. But for these, an evaluation of the amplitude, the size of the vibration, and the difference between a quake of 4 and 5, and that would be 10 times greater in amplitude and 35.5 times greater in energy release. So if you had an earthquake at the same place, so the same depth, and one was a 4 and one was a 5, the 5 would be 10 times greater in amplitude in the measure of that deal, and 31.5 times greater than in the energy released. So it's logarithmic, thing times 10, and there it's 5 times 31 times 5. So, for example, 1906 San Francisco earthquake, they estimate, they didn't have all the materials that we have now, but they estimate 8.25 on the Richter scale. That's what that San Francisco earthquake was. The Loma Prieta, 1, happened during a baseball game. You could have been watching that thing, and all of a sudden it was shaking. 1989, it was 7.1. Okay, the 1.15 magnitude difference, that's between the 7.1 and the 8.25, in these two quakes resulted in the following. The 2006 earthquake was about 14 times greater in terms of ground shaking, and about 53 times greater in terms of energy released. So this was significantly more, not just a little bit more. Well, 7 to 8, that's pretty small. No, it was a huge increase. So, and these were earthquake comparisons that I've used and I've seen other people use